All right, class, today we're going to be studying section 5.4, logarithmic functions in their graph. We're going to be able to graph natural and logarithmic functions. Log functions are the inverse of exponential functions. So if you notice here, we have the function f of x equals 10 to the x power, which is a exponential function. Now, if we remember our laws of inverses, an inverse is always flipped over the line y equals x. So here's our original exponential function, and our logarithmic function, or the inverse of that, would be g of x down here. In this particular case, the equation of g of x would be something similar to the log base 10 of x. Unlike exponential equations, your three important points occur where y equals -1, 0, and 1. And here's why. Sometimes it's hard for us to be able to graph a logarithmic function that we just plug in x values for and get out nice whole numbers. So how we like to think of these is, first, let's think of them in terms of what their exponential equivalent would be. So if we do our circular rule, we have a base of 10 to the y power equals x. So when I go through and find my important points, I'm going to plug in numbers for y instead of x, because in this inverse function, y happens to be the dependent variable. So if I plug in -1 for 10, I'll get 1/10 for x. If I plug in 0, then again I get 1, and if I plug in 1, then I get 10. And so my parent points still go x and y, so 1/10 -1, 1 and 0, and 10, 1. The same holds true with natural logs. I can also find my parent points for natural logs. Again, I'll apply the circle rule and say e to the y power equals x. This graph will be a pure approximation because e to the -1 is just 1 over e, which is a very small number. 0 is still 1, and when I plug in 1, I get e, which is about 2.7. So if we ever come across the situation of having to graph an ln, we'll have to do some approximating, and that's okay. Shifts of logarithms work the same way that exponentials do. You're going to have a number being multiplied out front. This is your y stretch. So you multiply this number to the y's. You also have an x stretch, or a horizontal stretch. You multiply this number to the x's, but again, you always multiply by the reciprocal, 1 over b. Then you have your shift, your horizontal shift, left or right, opposite of the sign. And then our vertical shift, up or down. And that one always moves the same as the sign. So let's do one. All right, first let's consider our parent function, which would just be, without any stretches or shifts, y equals the log base 2 of x. So if I'm evaluating a logarithm, I need to consider the exponential form. And instead of plugging in -1, 0, and 1 for x, I'm going to plug it in for y. Because in this form, it's just a little bit easier for me to work with. So if I plug in -1 into my parent function, I get out positive 1/2. If I plug in 0, I get 1. And if I plug in 1, I get 2. Let's plot those parent points. With logarithmic functions, you are going to have an asymptote as well. So I've got the point x equals 1/2 -1 for y. I have the points 1, 0. And I have the point 2, 1. So this part of the graph is going to extend on forever, increasing fairly rapidly, not as necessarily rapidly as an exponential function. Now, for example's sake, let's plug in some more negative numbers to watch the behavior of the graph. If I plug in -2, 2 to the -2 power is 1/4. If I plug in -3, 2 to the -3 power is 1/8. Notice how my numbers, my x values, are getting much smaller as I plug in bigger y values. That tells me that I have an asymptote of my parent function on this vertical line, as opposed to a horizontal line with the exponential function, which makes sense because they are inverses of each other. You won't necessarily have to do this for every single graph you do. This is just for our example. So now let's look at our stretches and shifts. I'm looking for multiplication first because I need to stretch those numbers. So 3 means that I multiply the y's by 3. So every single y value gets tripled, so this becomes -3. This stays 0, and this becomes +3. In this case, the asymptote has not moved for my stretch. So 1/2 -3, 1, 0, and 2, 3. So now I'm starting to increase a lot more rapidly. And then I'll do my shifts, if I have any. Looks like I have a shift with the x. That means that I'm going to do the opposite of +4, so that would be shifting backwards or to the left 4. Since I'm shifting to the left 4, my asymptote also has to shift. So I'm going to shift my asymptote first, 1, 2, 3, 4. And now I'll shift each point over 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. And this would be my final graph. This seems like a good place for us to stop for now. Please write down any questions you have, and we'll go over them in class.